I'm Tim Ventura, and we're joined today by John Storrs Hall, known to his friends as Josh, a subject matter expert and key influencer in the field of molecular nanotechnology. Josh is the author of Nanofuture, What's Next for Nanotechnology, a fellow of the Molecular Engineering Research Institute, and research fellow of the Institute for Molecular Manufacturing. His achievements also include former roles as a computer systems architect at Rutgers University, the founder of the Nanotech Usenet news group, founding chief scientist of NanoRex, and former president of the Foresight Institute. He joins us today to discuss a variety of visionary concepts for nanotech nuclear energy in his latest book, Where is My Flying Car?, available on Amazon. So Josh, welcome, or I should say welcome back, sir, and thank you for joining me again. We recently did an interview on your foundational work in nanotech. So today I want to explore some of the ideas related to nanotech and nuclear power that you discussed in Where is My Flying Car? So let me start out though a little bit more generally. What inspired you to write the book?
Well, to begin with, all the stuff I was doing at the Foresight Institute, one of the particular things I did was there was a group at NASA Ames who was interested in nanotechnology and who are friends of the Foresight people. But they wanted to try and get the rest of the NASA people, the old-time aeronautics types, to be interested in it too. And so they came to us at Foresight, and Eric Drexler and I did a little study as to what you could use nanotech for if you were building a flying car, or in fact any flying machine. But you know, the flying car seemed to be the cool, sexy sort of thing to do. And so we had a lot of fun doing that. And then the group at NASA kind of got canceled because of the politics surrounding nanotechnology under the National Nanotech Initiative. And I was thinking, you know, how can that be? What's going on here? And I decided to try and scope that out as a larger question. And so, having been introduced to flying cars by virtue of this process, I also got introduced to what I call the Machiavelli effect due to this process. And that is essentially, I sat down and put that in historical context, and I found that it had longer legs and deeper roots than I had realized. But that's sort of the basis of my getting interested in that and writing the book.
Okay. Well, so I want to focus only on one part of that. This is a big, expansive book. You have a lot of stuff in here, and I will put a link to this in the interview notes so that people can read this. I got the Kindle version. It's a wonderful read. There's a lot of great information in it. But I want to focus today on nanotech nuclear. That was actually the reason that I got the book. And you have a lot of really amazing information and ideas in there. So you'd written, and again, in this section on nanotech nuclear, and there's a lot of it there. This is your future projects part of it. There's something like 4 billion tons of uranium dissolved in the Earth's oceans. And that works out to 100 quadrillion watt years of energy, enough to supply the American 10 kilowatt level of power to 10 billion people for 10,000 years. So this is a ton of energy. And again, this is uranium that's already dissolved in the oceans. So can you tell me a little bit about this, and how can we use nanotech to extract this?
Well, the really interesting thing about it is that it's sort of at a few parts per million level of precedence or prevalence in the ocean. And the amusing thing about it is that we actually have the technology to get that out now. And if there's something that's dissolved, I mean, famously, the Nazis were trying to take all the gold that was dissolved in seawater, and there's a little bit. But the technology has advanced significantly since then, and uranium could be a lot more valuable than gold. So you can get it out by essentially you make this chemical stuff and you make sort of artificial seaweed, and you sprinkle it out and let it float around and then you go out and harvest it and process it and get the uranium out and put it back in. But the thing is that there's two aspects to this that are interesting, and one is that we can actually do that and economically recover parts per million of stuff from seawater. But the other one is that you get a really minor amount of uranium out, and it's worth something because uranium as a fuel is 1 million to 10 million times as much energy per weight as chemical fuels. And so if you're going to power a nuclear reactor, you need to dig up 1 million times less stuff than you do for fossil fueled engines and stuff that we're used to. So instead of having 400 tons worth of jet fuel in your jet, if you could capture the energy in uranium, you would have basically a piece the size of a domino that would easily fit in the palm of your hand instead. And that's the promise of the nuclear energy, and in fact of the original atomic age back in the 50s, after they had managed to produce working reactors and bombs and so forth in World War II. But so the thing is not that there's so hugely much of uranium in the oceans, although there is. It's that the nuclear fuel is so powerful that you don't really need a lot of it. And so the nuclear power gets economics that are similar to so-called renewable energy, because the fuel is essentially negligible. I mean, as a cost of operations, there's so much energy in uranium that no matter how you get it, you dig it up in mines in Canada, the ground in Antarctica is all full of it. There's lots of it in the Western United States, and basically nobody really worries about getting more uranium because the amount we have is already way more than we need for the immediate future energy needs.
Yeah, yeah. So that you've touched on a couple of big things, right? And I think one of them is, like you'd mentioned in World War II, trying to extract gold from the oceans. So one of those ideas could be, again, you talked about seaweed, also some kind of an artificial nanotech type seaweed to absorb uranium from the water, and you could take that out and process it. You might be able to do multiple rare earth materials, right? Multiple rare chemicals. So you could
very likely. I don't know offhand which ones of the rare earths and all that sort of stuff that actually do dissolve in seawater. It turns out that uranium does, but thorium, for example, doesn't. We still have more thorium than uranium. It's just 4 times as common in the Earth's makeup. So I mean, you don't even have to even think about uranium. You can use thorium, which is 4 times as common. I mean, there's lots and lots of choices here. And I mean, basically, you just look around and if you can do nuclear things, there's just energy coming out of our ears.
Yeah, yeah. Well, and you'd also written that there's even more uranium in the ocean rocks, and so these levels of dissolved uranium are basically a homeostatic equilibrium, right? So if we extract it, those levels will bounce back to current levels over time.
Yes, that's true. But I mean, if we really got into that in a serious way, I doubt that's what would happen. People would just go and mine the seafloor. So if you have parts per million of a nuclear fuel in your ore, it's like having the whole ore be a chemical fuel. It contains that much energy. And I think the typical average of uranium in the seafloor is about 5 parts per million. So it's got significantly more energy in it than if it were made of pure coal. and you're going to burn the coal. So it's just sitting there waiting for it to pick it up and process it and then do what you want. You can take it and build islands or leave holes in the ocean floor to reduce sea level rise, or whatever you want.
Yeah. Well, so in terms of the energy source itself, you've identified the fuel source. The next challenge is the reactor. And you've proposed in the book, you've talked about Freeman Dyson's TRIGA design. I wanted to touch on this because this was the reactor of choice. You outlined a lot of reasons why. I'm wondering if you could describe some of those for the audience.
Oh, the key, well, TRIGA is actually an experimental design that was done way back when, but it's been so reliable. It's been used for mostly university research reactors ever since, and it has a nice long history of no significant accidents. And the trick is that it's walk-away safe. I mean, you can pretty much do anything to the controls and then walk out, and nothing bad happens.
Oh, okay. These are, now you've written that these have a negative coefficient of reactivity. So the hotter the reactor gets, the less it supports the fission reaction. As you just mentioned, there are about 70 TRIGAs that have operated for over 60 years without a significant accident. So during this same period of time, I mean, with traditional reactors, we've gone through 3 Mile Island, Chernobyl, the recent Fukushima accidents, using these traditional reactor designs. Why aren't we using TRIGA reactors for all nuclear power generation?
Well, it wouldn't be TRIGA per se, because that was intended as a research reactor, and it doesn't generate energy. It's for doing high-level research in nuclear physics. But it is possible to design power reactors that do have the negative reactivity that you talked about. That would be a lot safer in the case of some kind of an accident. And it turns out that there's lots of different ways to make it walk away safe, and several of them are being looked at. Unfortunately, right now the main problem is the NRC, the Nuclear Regulatory Commission, that is requiring. I mean, for example, there's a company called Terrestrial Energy, I think, that is trying to push a small modular factory-built reactor design, so you don't have to get an entire new licensing process for each individual new reactor. And they're trying to get the design certified by the NRC, and they paid, I kid you not, $500 million in paperwork alone for the application. I mean, this is the sort of thing you have to go through if you want to build a nuclear reactor in the United States today.
Yeah.
So it's just a pain, and it's a case of major arteriosclerosis in the social system.
Well, so you've written that these reactors, this type of reactor, is capable of being miniaturized. So, and one way to do that is switching the fuel to plutonium. That allows you to scale it down to only about 1 foot in diameter, if I remember right. But you're also looking at some nanotech applications. You wouldn't use necessarily a reactor for those. That would probably be a very different style. What kind of scalability is there for nuclear energy?
Well, that 1 foot size is about as small as you can get with a neutron mediated chain reaction of the kind that all of our fission reactors, using one fuel or another, they all work by a neutron mediated chain reaction, some fast neutrons, some slow. But the thing is that there's a kind of a built-in limit to what you can do with that. You couldn't really power a small vehicle like a car with a reactor, even if you could pack it with a foot, because you have to put enough shielding around it because of the neutrons. Neutrons are hard to shield. So you're going to have to like a big brick wall anyway. And so once you're doing that, you may as well make the whole thing the size of a large building and make it powerful enough to light up a whole neighborhood, because you're going to have to build a building anyhow. And so that's basically the economics and logic of current nuclear reactors. And you can make them smaller. I mean, you could make one easily that would go into a shipping container. By pushing, you could make one that would fit into a phone booth. And in fact, NASA is doing those for use in long-term space missions. They have some designs, done by people that know a lot more about it than I do. But the thing is that you really want to get over the problem, which is that we have just dropped the ball in nuclear physics and research for 50 years. And ever since the 70s, the nuclear field has been moribund, and if you had, I remember how big a computer was in 1960. I mean, it was literally tons, and in current day terms, it had almost no memory and almost no processing power. It was just barely there as a computer. And yet nowadays we have computers literally a billion times as powerful as that, and you carry them in your pocket. Imagine that nuclear power had somehow managed to have the same trajectory, that the state of the art, the understanding of what could be done, and the techniques that we had, the technology, had improved at the same rate. You'd be carrying a nuclear reactor around in your pocket. I mean, that's sort of what the Jetsons were supposed to be. All the kind of power that now or then came from huge giant buildings, were available, in your pocket. And that was the sort of the promise of the notion of the atomic age. And it wasn't that we were going to take the big nuclear reactors that we had then and that we still have now and do something with them. It was that we were going to learn more, and we were going to get better, and we would have new designs and discover new physics and understand how to take advantage of the energy that we know is there in these nuclear fuels and use it by methods that we don't necessarily know, certainly didn't know then, and we can only vaguely guess at now. But that's the background and the promise of the atomic age.
Well, how does nanotech play a role in this? Again, that's definitely your specialty area. I mean, and I know that nanotech can be an enabling factor across the board when it comes to nuclear stuff. But have you given much thought to how nanotech could specifically help enable safer, smaller, more powerful nuclear technologies?
Oh yeah. Well, for example, if you want to make the smallest possible reactor, you have to come up with something like californium, which is a completely synthetic element that's produced in either nuclear reactors or particle accelerators. But it's only produced in microgram quantities. And you need a few ounces of that to make a nuclear reactor. And the reason that you can make a really tiny one has extremely high neutron capture bandwidth. They measure the neutron capture cross section in radioactive materials in barns because it's sort of like hitting the broadside of a barn. But it just has this huge capture cross section. And so you don't have to have that much of this stuff to be able to catch most of the neutrons and make the chain reaction go. Problem is that the way you get to this stuff in any of the other synthetic elements that we have is by shooting neutrons at other stuff and having them turn into the stuff. And so you have to take something that almost by definition does not have a high neutron capture cross section and bombard it with neutrons until you hit one just right and it turns into californium, and And you now have something that has a very high neutron capture cross-section. Well, if you're doing this statistically, you're almost certain to ruin your californium before you get another one out of your raw material, whatever you may be using. And so you have to do it one atom at a time. You have to take one atom and be able to tell if it captured the neutrons properly and underwent the isotopic change, and then get it out of the way before you shoot more neutrons there. And that's something only nanotech can do. You just can't do that with bulk methods. The other thing is just the basic essence of nanotech in the first place, is that you have, because you're working at atomic scale and you can have machines go very fast and process stuff about as fast in terms of how fast it moves through the factory. 10 miles an hour or so is typically as fast as stuff goes through a factory. We can go through a nanotech factory that fast too, because that's the way the scaling laws of engineering work. But the factory is only a couple of microns wide, so it goes through it, from stem to stern a lot faster. And it's that transit time that tells you what the value of the factory is, how fast it can reproduce another factory of its own size. So we're looking at things that have the reproduction time of bacteria, minutes to hours, instead of years, which is how long it takes a typical large-scale factory to reproduce itself. And so the productivity of a nanotech-based economy would just be orders of magnitude higher than the productivity of modern bulk methods of production. In the case of isotopic separation, which you desperately need for doing anything with nuclear, the various the ways that they have used to do isotopic separation range from, like, the stuff they built at Oak Ridge in World War II when they were trying to build the first atom bombs. They built an industrial facility larger than the American auto industry, in secret, sucking up huge amounts of power from the TVA dams. And basically what they did was that they had these machines they call calutrons that vaporized uranium and sent them through a mass spectrometer, and they came out and you could just barely separate the U-235 from the U-238 on the other end. And this was an ion beam. And so they produced micrograms of material, and the machines that were doing it weighed hundreds of tons. You may remember the cute story when they needed a huge amount of copper for the magnets, the electromagnets in the calutrons. And there wasn't that much copper available in the country because it was wartime and copper was critical. Well, they borrowed 14,000 tons of silver from the mint, made the wires out of silver. And then after the war, they gathered it all back up and gave it back. But that was one of the cute war stories that they actually, and that was just the wires, 14,000 tons of silver. Well, how long would it take you, if you're getting a microgram a day of stuff out of your machine, to reproduce the machine if the machine weighs 100,000 tons? Okay, that's the difference in processing rate that you're going to get between a nanotech and a bulk technology isotopic separation facility. So basically, if isotopic separation is something you need, and is essentially, if you're doing nuclear stuff, you do, the nanotech is essentially the only way you can go that is anywhere near economically feasible.
Now, is nanotech, can it be directly powered by nuclear materials, like beta emitters emitting electrons to you know, or is that something that's better left on a little bit larger scale?
Well, you could. I mean, basically, you're not going to have one atom and you're going to sit there and wait for it to go boom, because when it does, it's going to wreck your little nanomachine. But you could easily use beta emitters, especially a weak beta emitter like tritium, in nanomachines, and it would be perfectly reasonable in size. What I hope for, and why I think there might be a nanotech-enabled second atomic age, is that one of the things nanotech will be very good for is building scientific instruments and doing further research in nuclear physics and understanding a bunch of this stuff. If we could figure out a way to take a radioactive atom nucleus and nudge it so that it went off when you wanted it to, and especially nudge it in the right direction so it went off. And so the beta, for example, was not only emitted when you wanted, but in the direction you wanted. Then you have something. I mean, basically, you know, all the dreams of science fiction over the 20th century suddenly come true, because that you have the ability to, without using neutron mediated fission, you have the ability to capture nuclear levels of power density, and then you can put it in your car, and then you can actually put it in your pocket knife and have a pocket chainsaw, and you know, all this sort of stuff.
Yeah, yeah. And you know, I've actually done I've done stories on that. The idea was called stimulated beta decay, but stimulated nuclear decay. And it, I don't know. Officially the physics isn't there for it, but you know, well, my research showed that there may be something. Maybe we're moving towards it, and it'll be officially discovered. And
yeah, well, it's definitely not here now. Nobody knows how to do that. There are ways that we know that you can modify the decay rates of some elements, but right now they take more energy than you get from the element. On the other hand, what they tell us is that the physics could be there, and yeah. I have hopes for something of a new age in nuclear physics, simply because we've dropped it. We haven't been working on it for 50 years. And if we turned around and said, okay, this is something we need, and it became popular again, and people started putting, oh heavens, if we were to put as much intelligence and work and so forth into nuclear physics as we currently do in web page search optimization, you know, we would have a Jetsons world right around the corner. Right now, we don't do that, but we could, and one of my main messages is that we ought to be.
Oh yeah, yeah, absolutely. Well, and so I want to touch on this. You didn't just write about fission energy. You also wrote about cold fusion, or low energy nuclear reactions, lattice confinement fusion, and then you also wrote about hot fusion as well. But I do want to touch on cold fusion, if that's okay. Is this, do you believe, a viable method for generating power? Is there something there? This has been highly debated. And then lattice confinement fusion is yet kind of another related spin-off, right, on that. Yeah. Could you touch on that a little bit?
Oh, sure. The thing is that right now we simply don't know what's going on in the cold fusion experiments, and we do have enough experiments, and people have been doing you know, at low funding levels, but you know, a significant smallish scientific field of low energy reactions has been going on for 30 years now. And so there's very little doubt that there's something going on that the current theories don't explain properly. There is a lot of doubt as to whether any particular technique really is worth pushing, because most of the experiments are sporadic and low power, and almost everybody who has this great idea, they go and they get a gadget that works, and it may work for a day and it may work for a year, but then they try to build another one just like it, and it's not like it and it doesn't work, or it only works at 1% the power levels, or something like that. And the only reasonable explanation is that there's something going on at the level of matter that approaches the micro or nanostructures in materials. I mean, how many atoms there are to a grain of the metallic substrate, for example, and there's just a huge amount of stuff that we don't know about what goes on at that level. Just that physical level of size with the materials we have, much less being able to make active machinery, which is what nanotech would be. And so it basically, I'd like to compare the stuff they do that is now called nanotechnology to having a dump truck full of Legos, and you go along and you dump them out, and you have all these fancy brushes and all this sort of stuff, where you're able to have the Legos fall out of your dump truck and form a layer of Legos on the ground that it's only one Lego thick, right? That's current nanotechnology. Real nanotechnology would be being able to take all these same Legos and actually building things with them and putting them together in exactly specified ways, and building usable shapes and machines and all this other stuff that we know that we can do with atoms. And then at that point, you get the productivity takeoff, and you get the ability to control matter at any scale we want, and most importantly, the ability to do experiments that show you what effects happen when you have certain concentrations and certain configurations and mechanisms at the atomic scale. And then you can say, okay, this is going to do cold fusion, or this isn't going to do cold fusion, and so forth. But right now, we just don't have the technology to experiment properly. And so we really don't know what's going on down there.
Well, and it's interesting also. I've read it, and lattice-confinement fusion is all about these nanoscale structures. But in terms of LENR, one of the things that I've heard is probably a dozen different variations on this theory that you're taking protons, you're pushing them into the cracks in the anode and the cathode, and as the crack gets smaller and smaller, maybe possibly it's pushing them together and overcoming the Coulomb barrier. You'd mentioned in your book Peter Hagelstein's quantum coherence theory that might explain that. But what interested me about that was all of these things work on that nanotech scale. I mean, with traditional nuclear energy, I think there are a lot of ways that nanotech can enable and facilitate that, right, and make it more efficient. But in terms of cold fusion, it seems like the whole thing is working on that nanotech scale.
Absolutely. You got to, okay, first off, we know that quantum coherence works because that's what lasers are. I mean, this is a very basic part of our technology now. The trick is, can you do quantum coherence at the nuclear scale? Can you find couplings in the equations between, for example, heat can be observed as a quantum phenomenon, and it's called phonons when you do, and they're waves in the quantum mechanical wave function. And so in theory, if you do the math right, you should be able to find some place where that wave and the waves of stuff that we think of as being nuclear forces interact somehow. And that's what Hagelstein thinks is going on in the cold fusion, because the main problem with cold fusion is not so much actually pushing your protons together, or proton and some other nuclei. It's causing the resulting nuclear reaction not to simply go kablooey and blow up the atom, but rather come out as gentle heat, which appears to be what's happening in the cold fusion experiments. Now, in fact, it can come out as a lot of what we consider big heavy heat, but the fact is that that's compared with nuclear energy densities. You have to knock it down to get into the realm where you're not literally vaporizing your stuff by a factor of 1 million. You have to take that energy and spread it out over at least 1 million atoms before letting loose of it, and that's something that's theoretically interesting, difficult, and possible, maybe.
Yeah, well, and that's an important point also. I've done some interviews on hot fusion, and one of the issues there is, the neutrons coming out of these things are high speed, high energy, and they're going to degrade all of these shielding structures over time, right? And so that's one of the issues is I think with anything nuclear, because you're dealing with so much energy and you're dealing with almost like these little projectile shotgun events on a nuclear level, right?
In particular, anything nuclear that is mediated by neutrons. Yeah. I mean, if you had the like say the proton boron 11 reaction that ultimately produces 3 alphas, it's all charged particles, and you can contain it and harness it with magnetic fields. Okay, so that's a lot easier to deal with if you could get it to happen than stuff using neutrons, because you just can't contain neutrons. They go right through you like neutrons.
Yeah. Well, so you've written about the Navy Spa War experiments that showed radiation from a cold fusion experiment. Would you say that is kind of a proof that something is?
Oh yeah, there's plenty of proof. If you go and look at the literature, there's reports of all these experiments which are very, very difficult to, especially in mass. It's very difficult to say none of these work, even though there might be some experiments. But and there's some pretty simple experiments that basically back in '89 during the cold fusion original furor, NASA Glenn did an experiment where they just fed hydrogen through a hydrogen filter, which was made of palladium. Solid metal palladium is a good hydrogen filter. It goes in one side and comes out the other, but nothing else does. And they did it with ordinary hydrogen, and then they did it with deuterium. And the thing heated up to 20 degrees hotter when they used deuterium. So I figured something cold fusion like was going on. It's a very simple experiment. Nobody is going to try and make a usable heat engine with a 20-degree temperature rise, especially with stuff as expensive as deuterium and palladium. I mean, this wedding ring you see here is palladium. And it's a precious metal. So, but for scientists, this is something that ought to arouse their interest. And there was quite a bit of Machiavelli effect that had to happen to keep people from being interested in that. And it was not the same as, but very similar to the backlash against nanotech that I was personally acquainted with. And so I said, well, maybe that's what was happening, and it was definitely worth a second look. And so when I did a second look, I thought, yeah, oh boy, it's got the Machiavelli tracks all over it.
Yeah. But I think in general, it is intriguing because when you're working with things on that level, and again, nanotech is all about moving atoms around, moving molecules around, moving these tiny bits and pieces, right? As you mentioned, the Lego blocks, and putting them together in unique and interesting ways to reach these effects. Cold fusion seems like it's right on that level. So if there is something there that can be harnessed, then it seems like that would almost be perfect for nanotech.
Yeah, if 1 in a million tiny nano cracks in a piece of treated palladium turns out to act like a particle accelerator, which is what some of the theories are. You should be able to build the actual particle accelerator at the same scale and get it right every time, rather than just 1 in a million and go through all these crazy material processing things that sometimes possibly maybe work. So that's the thing about nanotech and cold fusion or any nuclear application, is that the stuff that we know works and the stuff that we have to jump through hoops to get to happen in a bulk piece of material, we'll just sit down and build. I mean, we'll lay out the plans. We'll say this atom goes here and that one goes there, and boom, you have your microscopic particle accelerator that then feeds the opening end of some nuclear reaction.
Yeah, yeah. Well, now you also did write, you put a lot in the book about hot fusion. I don't know if we have time to touch on that too much, but this is a big money research area, right? I mean, this is the one that involves all the scientists, lots of, multi-billion-dollar projects. There's a lot going on there. The progress towards commercial viability has been slow. Do you see a role for nanotech in hot fusion?
Of course, it would a role from nanotech in any major technological pursuit, but I don't think that much about the prospects for hot fusion in the near term. I think that ultimately, given what we have in the universe for fuel, people are going to start doing that. But I mean, I would really like to see people understand the process and the physics well enough to use nitrogen as a nuclear fuel, because you fuse 2 nitrogen atoms, you get a modest amount of energy for an atom, and your waste material is just plain silicon, i.e. sand. And there's your fuel. All of the, now 80% of the air is your fuel. Talking about fuel you can't run out of, because again, this is a nuclear process, and you're using tiny amounts, even of your nuclear fuel. So I'd like to see a lot of research into stuff like that. I mean, right now the process that they're looking for hot fusion involves using deuterium, which is, you can come by it. It's a tiny fraction of seawater, but it's there. And tritium, which is only produced in nuclear reactors and costs $30,000 a gram. So this is not going to be the be all and end all of the energy crisis. It's full-time employment for a certain brand of nuclear physicists and so forth. And I'd be the last one to say people shouldn't do that, because I think they should. I think there should be more interest in nuclear processes and nuclear science and all of that. And who knows what's going to come out of this. And some of the people are even trying that proton boron 11 reaction I was talking about earlier. But I certainly don't expect to get any power on the grid from a fusion reactor in a decade, maybe not 2 decades.
Yeah,
I mean,
yeah.
they're just not nearly as close as the hype makes them out to be.
But again, you'd mentioned nanotech for isotopic separation, and so potentially maybe you could use nanotech for basically concentrating deuterium, concentrating all of basically the specialty gases, right, that go into fusion reactions. And so
yeah, and a whole bunch of the rest of rapidly progressing technology, noticeably computer simulation of the machines and the processes, and trying to keep the magnetic instabilities from creeping in and so forth. And I mean, the latest that I've read is essentially that at the moment, the inertial confinement, i.e. the things where they have a gazillion super hot lasers and blow up this tiny little sample and make a tiny hydrogen bomb out of it, is more promising than the stellarators and the tokamaks and the magnetic confinement. But in either case, you're still looking at least a decade before you get any payback at all.
Well, yeah, and that was one of, I feel like I misspoke earlier when I was saying progress is slow. I'm actually I love fusion energy. That's something that's really intriguing to me. There's actually been a lot of progress, and it's been happening very rapidly. The overall progress towards commercialization has been slow, right? And so I've heard people say something like fusion it's been 20 years away for the last 50 years or something like that. So.
Yeah, well, one of the things I point out in the book is that you get a lot of support from certain sectors for fusion simply because it's unlikely to happen soon, and it's unlikely to be a big change in people's lifestyle. It's not something that's suddenly going to make power cheap again, and not something that is going to get us back on the Henry Adams curve and that kind of thing. And so it's a good way to say, oh yeah, I'm for energy. It's just that it has to be, this kind of clean, this kind of cheap, this kind of environmentally benign. Well, the thing is that these same people, in my understanding, are not really interested in that. They're really interested in keeping you from getting energy. And that as soon as you suddenly get a pathway to working fusion energy, especially if it's the deuterium tritium reaction that everybody is playing with right now, they will suddenly discover that it produces just these huge copious floods of neutrons and that they're horrible. And it will be castigated just as much as fission is.
Yeah, yeah. Well, I hope that's not the case. These are energy sources the world desperately needs, and I mean, I think all three of these have tremendous potential. I think nanotech has the ability to, again, enable and facilitate these. At the very least, it could make them more efficient. In the realm of potential applications for cold fusion, it may be what facilitates the creation of it in the first place. So there's so much here, and the energy densities are what, as you mentioned many times, the energy densities are what make this so exciting for humanity's future fuel. Well,
Yeah.
Josh, thank you again for your time. I can't thank you enough for coming on and discussing this. This is pretty in-depth material, but I think it's so valuable to get these ideas out to people. So again, the book is called Where's My Flying Car? I'm going to put a link on this interview to that on Amazon. People can get that, I believe, in Kindle version. I think you have a hard copy that people can buy as well. So let me close by asking what some of your other future plans are. Are you still focused on nanotech, or are you moving to other areas?
I'm happy being retired and spending a fair amount of my time flogging the book, and but I'm sort of in the background. I'm trying to write a fiction, which I have never done before, and doing some robotics research, and basically playing tennis and having a good time.
No, that's awesome. That's awesome. Josh, thank you again so much, sir, and have a wonderful day.
Okay, happy to be here. Thank you, Tim.